So we are coming to our second MuniHac 2025 keynote. Our second keynote is by Andrew Lelechenko. Andrew, well, if you handle strings anywhere in your Haskell application, you really can't get around Andrew. He's the maintainer of both the byte string library and the text library. And also he's a former core library committee member and an active member of the Haskell Foundation. And no surprise, Andrew is going to talk about strings, but this time combined with linear types.
Thank you, everyone. All right, yeah, my name is Andrew. Today I'll be talking with you all about how to connect strings, right? And one technical thing, I know that it could be difficult to see the screen from some desks, so please, if you are in a position where you cannot see the slides clearly, use this QR code to download slides to your desktop, because there are quite a lot of code there and it will be difficult to follow otherwise. Right, so the topic is how to build a string, yeah, and to make it interesting, we will finish with using linear Haskell to do that. But before we go to this topic of linear types, let's probably start with something very basic, right? So as we know, like string in Haskell is just a linked list of characters, right? And the basic way to concatenate strings is use this plus plus operator. Could someone please tell me, is there anything wrong with this code? So I have 3 strings which I'd like to concatenate all together. Is it correct way to do so? Is it the right way to do so? It's true that it's linear, right? But what do you expect from concatenation? Concatenation has to do linear amount of job. It does it in linear amount of time, right? You cannot really concatenate strings in constant amount of time. You need to spend at least linear amount of time. So that's by on its own, it's not that bad, right? It's kind of expected. Let me give you 2 options. You can concatenate right and concatenate left. Which ones of them is better? Copying a list is not quadratic, right? It's linear. Like you copy a list, okay, you just go and copy it.
So I remember if you're linear in time on the first list, on the right leftmost list. So if you concatenate a very big list and a small list, it will take a very big amount of time.
Right, I think we are approaching the answer here. So first of all, what we need to remember is that plus plus operator is defined as infix right, which means that by default, if I write it without any brackets like this, right, it will associate to the right, so it will put brackets like here. And that's actually a good way to concatenate strings, because if you look at the implementation of how plus plus is defined, right, it's not doing anything with its second argument at all, right? It never even inspects it, never even looks whether it's a bottom or an error or anything. So yeah, as Hekate correctly said, like plus plus is linear in its first argument. It will do as much job as many elements you have in the first argument of concatenation. And so if you doing concatenation this way, you first spend as many time as long as this string, and then you spend as many time as long as this string. But if you do it this way, you first spend time concatenating long, and then you concatenate both long and very long, so that the length of the first string is accounted twice. So that's why you want to concatenate to the right. And you don't have to believe me, we can just test it, right? So I am concatenating 3 strings. I admit that 2 of them are not particularly long, but let's just imagine that they are. Yeah, and we can see that the difference between between the order of association makes like huge impact on both time and allocations. And if we look for really like catastrophic example, and what we usually mention when we talk that like concatenation of lists has an opportunity to exhibit a quadratic behavior, it's really when you concatenate lots of strings. Like in this case, like you see, I basically create 10,000 strings. All of them are 1 character long. And then I basically concatenate them to the right with fold right. And it's actually quite fast, like, and no problem with allocations. It's all quite reasonable. But if only I make a small mistake in one letter and concatenate things to the left, it explodes immediately, right? My runtime is basically 100 times longer. My allocations are how many? 1,000 times more allocations. Yeah, which is quite terrible. So like basic lesson in concatenation of strings is that let's all be very diligent and always make sure that we concatenate strings to the right. So we like kind of build our tail first and then attach our head to it. Everyone, of course, always excels and succeeds in being diligent all the time, right? No problem with that. And here is my data type user with 3 fields. Let's imagine for simplicity that all 3 fields are string, right? And here is my instance show, which for the sake of argument just concatenates all 3 strings together. I guess in the real world example, we would like to put some maybe fillers in between, maybe new lines or whatever, but the simplest case is just this. What's wrong with this definition of instance show? Locally, nothing. All right, let's be not that local. Here is my data type for order in my shop, right? It has some user who made an order and has some product name and, well, let's say date of the order. And I kind of keep going. I define show for order, well, kind of in a reasonable way. Yeah, what's going wrong now? Yeah.
My intuition is that with the show user, you're falling in the trap of left concatenation.
Right. Because this show user is these 3 things concatenated together. So imagine that I basically have brackets here and concatenate 3 things, and they can be quite long, like your address can be a long string, not extra long, just very long maybe. And only then you concatenate product and date, right? Yes, we exactly fall into the trap of concatenating from the left. Not entirely, but for the first part of this concatenation. And it appears that great ancients, the designers of type class show, actually knew about this issue. And if you actually look at how class show is defined, it has 2 operations. It has like a simple one, which is just show. And it also has this funny looking one, shows track. We'll skip what this first argument is doing. It's like a priority for brackets. Let's leave it out. But essentially it says that if you give me your element, your value a, and you give me string representing the tail of your desired result, I'll show a and attach it as a head to this tail. And so the correct way of defining instance show, and this is what GHC actually does for you automatically, so please all appreciate how helpful is GHC. Yeah, the correct way is actually define this show prec thing. Yeah, and basically if I write it down, it looks like this, that I basically have my user with some fields, right? And I have the rest, this string. And basically, and the definition is quite straightforward. I just know that my plus plus associates to the right. So the brackets are like this and like this. And everything will go together smoothly. And then when I need to define show for order, yeah, I also define shows prec, which takes this tail. And I say that, okay, so take this, the rest of the string, concatenate it with date and product, and then pass this thing here, right? And this is how we ensure, like in usual Haskell programs with derived show instance, that concatenation of strings always associates to the right, and we pretty much never fall into the quadratic trap. Now, it feels a bit kinda not symmetric enough, this thing. Like I kinda plus plus somewhere and then shows prec somewhere, and then this rest argument is kinda lingering around. So I can rewrite these definitions in a more concise way. Right, so now I'm basically talking about functions. This is supposed to be a function from string to string. And I say that this function from string to string is defined as a composition of three functions. One of them is please add phone, another please add address, and this one please add name. And then my definition for order also can be rewritten as a composition of three functions in a nice, neat way. And if, for example, my product or my date will also be not just string, but some more complex data type, yeah, I will also use like some appropriate shows prec here instead of just plus plus. And a neat thing about function composition, and kind of actually deeply magical, is this. We just discussed how important it is to associate to the correct side. So which of these snippets works better? Like you can see that in this case, I compose long plus plus and this. And in the second example, I compose this and extra long plus plus, and I apply these functions just to an empty list. It appears somewhat surprisingly after my introduction that there is no big difference. Because the second expression, when GHC will try to evaluate it in runtime, yeah, it will operate like on heap objects, and it will quickly rewrite it and memorize the result of this rewrite, basically passing a $sign instead of dots. And then what it ends up is basically that you have this function applied to something. And as we know already, like plus plus doesn't really look at its second argument before it exhausts its first argument. So kinda as soon as you write your show functions as a compositions, it doesn't really matter how you associate them. You will spend constant amount of time, like GHC will spend in runtime some amount of time basically propagating $ to the forwards, but it's just a constant and small amount, and it's not affecting it's not adding a constant factor, it's just constant amount of time, but not a multiplier. And this trick is employed by so-called difference lists, where you say that your difference list is function from string to string, and you say that you can create difference list from any string. Like you say that I just go and create function which prepends this XS, and that I can convert any difference list to a string, simply supplying empty string here. And then if I use this approach, I can basically get all my strings, convert all of them to these difference lists, and then I can kind of concatenate them left and right. I don't care because it's all function composition. Yeah, and then I will just call to string, and it will all work nicely, avoiding quadratic issues. One problem with this approach is that now you deal with functions here, like every object representing a part of your builder is a function thunk, and it's kind of a bit expensive, not too much expensive. We are dealing with it in Haskell. Haskell is functional language. Functions are actually relatively cheap, but it's not as cheap as having just some basically data in normal form, for example, right? It's a function. It has to be called, it has to be evaluated. It all takes a bit of time. So for lists, we have two options, like either we are very diligent and we always take care of the order of concatenation, or we sacrifice some performance, some constant factor, and we use difference lists, and then we can be negligent and kind of just lump it all together. It will work out. Right. So kind of for lists and for strings, problem solved. Nothing to do here. Thank you, everyone. The only slight wrinkle is that we really do not want to use lists and strings which are backed by list of characters in Haskell. Really, in our applications, in our real life, we want to use text. And everywhere I say text, I mean strict text, which is a data type which is basically just an array. Yeah, your old school like C style array of characters, just a piece of memory. So data type for text in Haskell, yeah, it's a record with 3 fields. So first one is just a pointer to a byte array, just a raw region of memory, nothing fancy. And then it has basically 2 additional elements. One says that one contains offset in that byte array, yeah, which says where my data actually starts. Because maybe maybe it was a huge byte array, and maybe I sliced it in a couple of pieces. So maybe my string doesn't start from the beginning of that array. Maybe it starts from some offset. And we also say that, okay, my string also has some length starting from the offset. All good, quite reasonable. There could be empty space in this buffer after offset plus length. So usually it comes from the case when you get your string from like file, so you have a huge byte array, and then you start like parsing it into pieces. Yeah, and then you end up with like slices of that huge byte array, and each of them is just small text with some small lengths and some offset in that huge amount of memory. And again, we are presented with 2 options how to concatenate things. We can concatenate to the right, we can concatenate to the left. Which one is better? Pretty much the same, yes. So unfortunately, and is it fortunate or unfortunate that they are the same? Are they both good or are they both bad? Yes, unfortunately, both ways to concatenate are bad. Let's just verify it. First of all, let's verify that there is no meaningful difference between the way you concatenate, left or right. So you can see that memory consumption, memory allocations are exactly the same. Yeah, time kind of differs a little bit, but not too much. And secondly, let's try our previous example of catastrophic concatenation, when we concatenate like 10,000 very short texts. So exactly the same example as it was before, and we try fold R and we try fold L, and doesn't look great, because you see like the results are pretty much the same. But if you remember my slide with the concatenation of lists, for lists, fold R was working under 10 milliseconds. And suddenly we replaced our inefficient list-baked strings with nice shiny byte arrays, and we are like 16 times slower. And there is no way around, right? Like kind of, nope. The reason is that indeed when you concatenate 2 byte arrays, you must basically allocate completely new amount of memory, completely new space, and then copy the first array there and the second array there. So if concatenation of lists was linear only in its first argument and didn't care about the second argument at all, concatenation of text is linear in both, because you have copy both byte arrays to a new location. And whatever way you do it, you end up like basically copying again and again. So like whether you do it this way, you first copy this X to a location where these 2 byte arrays will be stored, and then you copy it again when you allocate memory enough for all 3 of them. And absolutely the same will happen here. So it seems like we have a problem here, because kinda to concatenate efficiently, we need to know the future. Like if only we knew that, this will be concatenated 3 times, and we allocated like, immediately allocated like 300 megabytes byte array. Yeah, and we just copied like this to the first 100 megabytes, to the second 100 megabytes, and to the end of the array, will be perfectly efficient. But how can we guess what's the size of the final result? Like, can we have some crystal ball? Like maybe ask someone? Not sure. So there are 2 approaches. One of them is in the package text itself, which is lazy builder. And it kinda sidesteps the issue. It says, well, I cannot predict the future, sorry. I don't know what the size of the result gonna be, so I will not give you just a single text. I'll give you a list of texts, which is honestly quite a lot of cheating. Kinda, if I wanted to get a list, I would probably use lists, right? But it has no way around here. So the buffer here is basically just a mutable array with, again, offset, and it has 2 numbers. One says how many elements are actually allocated, and how many elements at the end are unused, not allocated yet. So we are kind of doing memory allocation by hand here, like kind of implementing our own malloc. By the way, I believe that the length of buffer is always equal to the sum of these 3 ints, and it means that we probably can shave off one of the fields and maybe get it faster. If someone wants to give it a try later today, I'll be happy to help with it. But Other than that, so how does this work? It again follows our pattern which we saw before. Like you give me what will happen with the tail. Like you remember we had functions which took like string from string, which will take the future, the remainder of the string, and will kind of add something at the beginning. So this builder works in kind of similar way. It says, okay, you give me the continuation in the first argument, and you give me some buffer to use, which is ready to use. And what I'm gonna do, I will write something there. Probably I'm prepared to write there some text or something. And if it fits in that buffer, then I will update used and unused counters and pass the very same buffer to this continuation, which will continue allocation pattern. If what I am employed to put there doesn't fit, unused is 0, for example, right? Everything has already been allocated. Then I will just pop out this buffer as a text. I can easily convert it to a text basically by just removing this last field. And allocate a new buffer and put my data into that new buffer and pass it to the continuation. The problem with this approach is twofold. So first of all, it gives me a list of text, and probably I actually still want to concatenate it all together into one single text. So it kind of doesn't solve my problem entirely. Secondly, it doesn't really know the future. It basically just says, okay, I will allocate buffers like 4 kilobytes long every time. And if you use this builder just to build maybe very short string, maybe, I don't know, like 10 characters, well, I still allocated 4 kilobytes. Yes, I then wrote 10 characters there, and I returned you the result. Yes, it will shrink unused bytes and so on, but still it kind of already spent lots of time allocating that 4 kilobytes. And on the other hand, like it can also underestimate what I'm gonna do. Because if I'm gonna produce like gigabytes of data, yeah, I can produce gigabytes in modern PC memory easily, right? And it kind of keeps allocating these 4 kilobytes, 32 kilobytes. Doesn't really help anyone. Like really, we need to get bigger. But that's because it doesn't know the future. Upsides of this style of lazy builders is that they can be used like for lazy I/O. You can start consuming data, you can start popping out data, like kinda in interleaving fashion. But I question how often you really need it these days. Like most of your data, most of the things you want to output can fit in your memory. And very often you produce this text not just to like stream it to a file, but you're actually gonna send it somewhere, call something which is not using a streaming interface, and you will have to allocate it in full. So that's kind of very lazy interface. The very opposite approach is text builder package by Nikita Volkov. I think it's been the first package using this approach to text builders. There are some other implementations on Hackage as well, but let's start with this one. It says that my builder is a strict builder. I will keep track how long my output is gonna be, and I will keep basically a function which given an array will write something there. And that's basically, we say that, okay, we will not start doing anything until we build our builder entirely, like concatenating things. We concatenate everything together. When we arrived with our final builder, it has this int. This is our future. Yeah, this is an estimate, an upper estimate of the size of the result. Then I will allocate this huge byte array and will call this function to write down all data, so that we write down one neat text large enough and no data is copied around twice. So when you concatenate these builders, right, what you basically do, you say, okay, I have one builder which says I expect that my contents will fit into length L, and this is my function which will actually write down my content. And the second builder which says I'm going to write up to length write bytes, and here is function which will actually do it. You can concatenate them and produce a new builder which says, okay, here is my estimate how much space I'm going to need. And here is my function which, given array and offset in it, will actually write down all the content. And it's all nice and shiny and actually works very, very fast. Usually better than a lazy builder in text. It satisfies our requirement that it gives us a single blob of strict text. But in order just to start working, it needs to know all the content and compute the size of the final result, which means that you kind of have to you need to force all your inputs, and only when you forced on all your inputs, you will be able to start putting them into your final byte array. And another concern of mine with actually both of these approaches is that in both cases, builder inside contains some functions. Again, Haskell is functional language. Having functions is normal, no shame in it, but it takes time. It's not as efficient as just having some raw data. And really, why are we always inventing the wheel? What does everyone else on this planet do when they need to concatenate strings? What does your Java standard library do? And kind of Java style string builder looks like this. Sorry, this is a bit of too many long function names. Let me try and guide you through. So we say that our buffer is just byte array, with a counter how many bytes have been used. And then we have trailing unused bytes. We can compute the number by taking size of byte array and subtracting how many been used. And if you want me, this is pure data, no functions, it's just raw lump of memory. And then if you want me to concatenate things, right, so I have my buffer, I have my text. As we discussed previously, text is represented internally as another byte array, offset, and length after that offset, right? So what do? I check how many space I have available, what's my capacity in this byte array. I thaw it, so I convert from immutable byte array to mutable byte array, which I will be able to modify. I just copy bytes from the text from source. I copy bytes from source from given offset to my mutable array. Freeze it back so that it's no longer mutable, and return you another buffer, right, with amended amount of used bytes. And if my capacity is not enough, then double the size. Then just basically compute how many bytes I'm going to need and double it. Computers are fast enough. Yeah, I double it, and then I copy my original content to a new mutable array, and then I copy my text, freeze things, and return. Because we double size of our array every time, it's like amortized linear time here. Yes, we can hit this case, but most of the time we will be in this case. If you imagine that we are kind of appending text of kind of the same or similar length, then after a couple of enlargements of our array, yeah, we will have enough space for quite some time to just write things there. So that sounds good, like everyone else does it, right? What's wrong? Unsafe. What exactly is unsafe?
Yeah, so I think it's unsafe because you're mutating your array, so you lose referential transparency.
Right. Can we unpack it? What is the the scenario when our data is corrupted?
When you have a second reference. When you have a second reference to this data that doesn't expect it to be changed.
Yeah, that's right. So basically, we kind of pretend that our buffer is just a usual immutable variable, and imagine that two functions somehow got hold of the same buffer. Yeah, and both of them decided that they will append something there. And indeed, both of them will go here, do this unsafe thing, write data, do another unsafe thing, and kind of pretend that it's normal. But in fact, both of them has just overwritten each other. Right, so in Haskell, we do not like this approach. Kind of in an imperative language, you would not expect anything different, actually. But in Haskell, we kind of expect what is called referential transparency. Yes?
But we could also, I mean, in Haskell, usually you would just keep it in ST, right? So you can have the type signature actually say that it's effectful. I mean, so it doesn't need to be unsafe. If you mark it as effectful, it will be effectful. And don't, because semigroup promises purity. This is not pure, so it should not promise to be semigroup.
Right. So yes, one usual approach what we Haskellers do is, let's be honest, this is mutable buffer. We need to work with a mutable buffer by passing state token S and work in stmonad. Works perfectly well. Like, this code is quite correct. Like, we are honest with our readers and with our users that this is a mutable array. And yeah, we basically don't have any unsafe operations any longer in this piece of code, right? We do all the same. We get size of this mutable byte array. We check if we can just write our text there, or maybe we need to double its size, right? That's perfectly valid code. So why don't we all just go and use it? What makes it inconvenient? Because if everyone is happy to use this code, I'm done for today.
We have many standard library features that are written in terms of semigroups. So we like to use the type classes we have available instead of using effects everywhere.
Yeah, that's one of the reasons. Basically, this stmonad popping out is very inconvenient. Yes, you cannot use your. It will get in your way at every turn. Yeah.
Another problem is that I don't know where STs define which module to import, and I would guess a lot of people don't either.
Right. For example, like if you want to work, yeah, one moment. If you want to work with two buffers at the same time, yeah, if you want to like deal with two builders, you would kind of have to manually decide in which order you are threading them, because you have only one this s argument. Yeah.
I just wanted to comment that this is the Haskell's version of the colored function problem.
I'm not aware what's this.
The fact that adding a monad at the end of your function means you can no longer use it with like standard library functions.
Right. Yeah, and if you happen to work in I/O, for example, good luck with dealing I/O and ST and converting between them. And if inside of your manipulations with your builder you want to thaw and freeze a vector, for example, yeah, you're also not doing well. So it's very inconvenient to work with this, and that's why we've been all looking for some workarounds. And if we kind of think about what could help us to deal with this like mutable state, you see, we don't want to poison our context. We don't want to poison our context with st. We'd rather somehow restrict our functions dealing with this mutable thing. So we kind of would like to restrict our functions to use this buffer only once and thread it only once. And that's probably many of you are suspicious. I'm hinting at linear types, because linear types are exactly the instrument which allows you not to poison your global context by restricting it to STS, but rather imposing local restrictions on your manipulations. And it appears the first attempt to use linear types for this problem is hidden in a dark corner of ettoparsec library. And it's 11 years old by today. So it's been implemented way, way before linear types appeared in Haskell. And the idea employed here is kind of cursed. Like, so you have your byte array and you have your counter of how many bytes you have used already. But you also have like a generation counter here. But that's not the entire story. You actually have another generation counter hidden into the first element of this byte array. So this byte array is not just your output. You need to remove the first. The first word away, and that will be your text. But the first word carries exactly the same number as this, like generation counter. And the idea is that if someone else has tampered with your byte array by unsafe operations and updated the generation counter inside, it will no longer match your generation counter outside. And you can catch this situation and say, okay, this byte array is, someone is tampering with it. I'm not gonna try and grow it any larger. I will just copy all the content outside and work with it in my new green field, hoping that no one will tamper with it. So here is a commit by Brian O'Sullivan like 11 years ago. And that's basically how I got interested about linear types. Because he says, yeah, like we use two generation counters, one mutable inside this byte array and another one immutable here, right, which track basically how many times we have touched this array. And if someone happened to like pass the same builder to two functions, each of them is trying to append something, yeah, we will catch it because these numbers will not be in sync. And in this case, we will have to do additional work, but hopefully it's not that often. It's not quite bulletproof because it's quite possible that you have that you run two threads concurrently and they can kind of both looked at byte array, check that it matches generation all good, and then started to mutate it concurrently. You kind of can work it around if you use atomic operations, and it's not that expensive nowadays, certainly. But then Brian makes this remark that like clients should never call a continuation more than once, okay? Yes, we need a linear type system to enforce this. I was reading this comment like a couple of years ago when I actually was upgrading Attoparsec to work with a new version of text, which I migrated from UTF-16 to UTF-8. And I read this comment and I thought, well, we do have linear types now, right? And with linear types, we probably do not need this generation counter. We do not need any atomic updates. And we probably do not need to do anything funny here. And it appears to be true. Like nowadays, we can just have your buffer with just your text inside. And if you are careful enough to thread it, you can basically implement all this Java style approach with doubling the size without compromising anything. Like the implementation of operations will be pretty much the same as on slides before, but now instead of being constrained to st monad, we will be constrained by linear arrows in our types. So I ended up writing a library, text builder linear, which implements this idea, which I kind of, well, stole from Java and stole from Brian O'Sullivan. Right, so there is very limited contribution from my side actually. So we defined our data type. You see, once you start like linear types, like a gateway types. Like when you start tinkering with them, you feel, well, maybe I can also have some unlifted types. So unlifted types are a special thing in Haskell. These values of unlifted type are guaranteed never to be bottoms. They're guaranteed never to be like not fully evaluated in a layman terms. So I say that my thing is unlifted. It has always be evaluated, and it contains a container buffer with a strict, with a forced field for text. Yeah, and that's it. There is nothing else there. That's just everything I need. That text, yes, I will manipulate that text and the byte array inside that text unsafely. I will kind of abuse it, and I will double the size of the buffer inside and do all this kind of manipulations which we just discussed in our Java style approach. But it all will be safely packaged here, because all my interface for buffers which I will expose to users will be constrained by linear arrows. So the working horse basically is function like this, which is quite similar to what you saw in a strict builder I presented earlier from Nikita Volkov's package. Right, you have to estimate somehow an upper bound for the length of content you are going to write. And you give me a function which is going to write this data. And then you give me one buffer, and I will, you see this linear lollipop arrow. And yeah, you give me a buffer and you give me lollipop, and I give you another buffer. So yes, what I am going to do, I'm going to go inside this text. I will very unsafely mutate it, right? But because it's all because of this linear arrow, we are guaranteed that no one ever is touching this. It's fine. We are guaranteed that there are no more references to the original text, and no one else can try and manipulate it. And then if you have this append bounded function, you can write this kind of operator, which will append a text to a buffer. So how to read these things? Like, you kind of have imagined that it's like this, that the arrow says that that linear arrow follows a linear argument. So buffer is consumed linearly, and text is consumed unrestrictedly. Yeah, there are no restrictions on text. You are free to use it later on, no problem with that. And that's kind of basic interface. So okay, how can I get my hands on this wonderful buffer? Like this magical thing which will solve all our problems. And the best thing is you don't. We will never give you this buffer. Because linear types, they restrict functions. You can never say that some value is linear by itself. Like if I give you this buffer, like there is nothing saying that it's linear here, right? No lollipops here at all. So if you ever get this buffer in your hands, you can do all sort of dirty tricks with it. You can indeed pass it multiple times to the same function and destroy it in most horrible way. So the trick to work with this kind of mutable arrays with linear types is that you never get to keep buffer in your hand. So the way you actually run it is kind of similar to what we saw just before, right? You kind of say you kind of need to produce some function, some linear function from buffer to buffer, and this magical function will just basically pass an empty buffer here. It will obtain a result, and then it will basically just go inside and extract this text. So you can see there is very, very little overhead here. This is just data, no functions here. Yeah, and this is doing pretty much nothing. One interesting consequence of this approach is that actually you can use the same buffer, well, the same kind of builder to produce text and byte string. It doesn't really matter for us. We can very easily just give you byte string if it's what you want, with the very same buffer. So let me give a short tour of functions available in this linear builder package. So we can append texts to buffer, we can append buffers to each other. If you append buffers, then they will consume both of them linearly. You can see two lollipops. If you append text, then there are no restrictions on text, but the buffer will be consumed. Right, and the way it looks like in your code is something like this. You see this run buffer takes a function, yeah, from buffer to like this, and it concatenates it nicely. Doesn't matter like how you put brackets here. Yeah, then one performance related thing is that very often in your program you concatenate with statically known strings. Right, lots of strings in your program are known at compile time. And luckily, GHC has a special representation for like raw strings statically known. It is like this. You just write your string and put hash at the end. And this will just basically allocate byte array like C style. Like you would not go to, you would never create any text, or even worse, you would never create any linked list of characters. And so the package provides special functions which allow you to concatenate with statically known literals. Yes?
So in you have a function that appends to buffers. In what circumstance would you have two buffers at hand if you're only ever given one and forced to always give it back?
That's a very good question. There is a function to duplicate your buffer in this library, but let's probably discuss it after the talk. But that's a very good question. Right, and yeah, you can append also just characters in straightforward way. Then we have a lot of functions which append numbers. I think I've got a bit little crazy with these operators, but I decided that if you can define custom operators, you must. So like if you have a bit of money, yeah, a bit of money, and it's finite, and it fits into finite sized number, yeah, you have this function. Why we care that it's finite bits? Because if it's finite, if your number type is finite, then we know in compile time its biggest possible size, right? If it's int, well, it cannot be longer than, what, 18, 19 characters, right? I don't need to look at your number at all. I will just like allocate 19 characters, and then we'll maybe write data there. But I know size up front, like upper bound is available up front without any introspection of the value. And then if you have lots of money, yeah, we have another function which is not that efficient as this one, but also quite good. Then if your money are hexadecimal, there is another function. And I don't really remember why it has this ampersand. What was the relation of ampersand to hexadecimal? Not that I ever knew about it, but now I have a good explanation. Thank you. Yeah, and then yeah, if you are calculating your mortgage and you have your percentage, you have a function to output it as well. Right, what else? Oh yes, of course. You see all this interface is very nice and shiny, but I would have zero hope for adoption of this library anywhere, because it's quite a jump from a usual builder to this linear style. So what I can do, I can actually kind of make a trick. I package this buffer to buffer linear function under new type, and then I basically have your usual functions which you would expect like for any builder, which like take text and give you this builder, take character, give you this builder, and so on and so forth. And then for this new type, I can have my usual semigroup instance, which just conveniently will compose functions. This is very nice for like migration. You basically just rename your imports, right? It's not very nice for performance because now you started to build this thunk of functions and this tree of functions all the way. Okay, so that's been the interface of this linear builder library. So how bad is our fancy performance? So this is benchmarks on my laptop. They might not necessarily be representative, so please do your own research. Yeah, and we benchmark like lazy builder from text, strict builder from text builder, and this linear builder. We have a couple of categories, so we can concatenate texts up to lengths of 1000 characters, up to lengths of 1 million characters. We can concatenate just characters one by one. We can produce decimal numbers, like 1000 decimal numbers all concatenated together, 1 million, hexadecimals and doubles. And it seems that performance is actually quite good. I'm not sure why. Maybe I'm benchmarking it wrong. One cheap trick which I employed here is that I'm benchmarking in this column, I'm benchmarking that linear interface, right, which is with linear arrows, which is buffer interface. And if I were to benchmark builder interface, which is more convenient and probably more like apple to apples with these other two contenders, then actually linear builder will get slower and in some cases, text builder will get into the first place. That's kind of a caveat. But I do recommend that if you go and use linear builder, then try and use actually the linear interface, because this is the one which offers you best performance results. And I guess that's all of it. Thank you all so much. You can find me in Telegram, you can send me an email, you can find this package at my GitHub and on Hackage.
Yeah, thank you so much, Andrew. Are there questions?
Yeah, I had a question. So before, if you were using the ST approach, you have to package everything and run ST in your code. But now if you are using the linear builder approach, don't you also need to define everything as a function and then run buffer? That was the...
You will end up, you will have to run your buffer, yes, but it kinda not poisoned by ST everywhere.
Okay, but you'd still have like this problem that if you have two buffers that you're working with, you have to divide your code up into two functions that will...
And not necessarily you can put it all inside of one function.
Okay. All right, thanks.
Right. Thank you for the excellent talk. I have a handful of things. Sorry. So, first of all, an observation. You were talking about the dots and more function composition being slightly slower, but that's as soon as you turn on optimizations, that will all completely erased by the compiler. So, just worth mentioning. The second thing is a question. So, text had this offset field, and I was wondering if you've ever considered something like advancing the pointer to the byte array itself, and then using something like a weak finalizer to guarantee that it's still garbage collected from the start of the array.
That's more like byte string works, because byte string is just a foreign pointer, no offset and length. And yes, when you slice byte string, you're just advancing that foreign pointer.
Got it. Right, and then lastly, a fun fact. So you were talking about unlifted types, and there are something actually that may impact performance. In that if you have a function which receives as an argument something which is unlifted, or actually, yeah, if you have a function and it receives an argument and it's not unlifted, then you have to check the code that's generated by the function has to check whether that thing is a thunk, and if it is, then go to the thunk. Otherwise, continue execution. But if it's unlifted and guaranteed at the type level, then you don't have to do the check, and the generated code will skip that check altogether. And if this happens in a hot loop, that means you don't even have to have code to enter a call. You don't have to have spilling, and that it can mean a world of difference in some specific scenarios. Yeah, thank you.
Yeah, unlifted types to the rescue.
Any other questions?
Just as a suggestion, did you benchmark what the difference is if you don't use the unlifted type? Because that would be very interesting.
That would be interesting, but I didn't.
It shouldn't be a big change, right?
Yes, it should be quite a small change. We can try it later today. There is a question there.
So if you're already going through the mess of having something that is not of kind type, why not unbox all the contents of text and make it a new type around the contents of text? Like use an unboxed product, basically.
Yeah, I think while reading the core program, I think it actually unpacks it good enough like this. Because like text field is strict, and I also kind of force it to unpack, and it ends up basically as a like just 3 fields without a header for text.
Yeah, it will be a pointer to an unboxed product that has the contents of the text. Yeah, there's worker wrapper, but that's an optimization. So the question is, have you tried out just using the completely unboxed?
No, I didn't. It could be an interesting opportunity.
Okay.
It's kind of nice, you know, just have the text there so you can just immediately extract it and show that that's it. But it's obviously not that difficult to build it back from unboxed representation. It could be more performant indeed.
So you have some figures on the speed up, but I wonder whether the speed up is depending on the size. Is it the amount of bytes, the amount of doubling we have to do, or is it some other metric that really decides when you really need this? Because I'm wondering, for example, when I would invest the time in migrating to this library. Is it about having, very big files, or is it about having a lot of small elements? We have other types in play also, like short byte string, short text, and so on. There are so many types here in play, and now we have another dimension, another API to choose. Basically, my question is there some napkin figure that I can use to find out when this is going to be a good investment?
I don't really know cases when it behaves worse than usual lazy text builder. It can behave worse than a strict text builder in some cases if you use builder interface only and for certain combination of sizes of strings, because you see, like, text builder is extremely efficient in case when it figured out the size of the result quickly, because then it will copy each piece of data only once, while this linear builder will waste some amount of time by basically doubling array and copying things.
So I was wondering if you're using this somewhere already, and if yes, then where, and if you can say, yeah.
I think I saw a couple of packages using this interface on Hackage. I haven't used it myself.
Yeah, actually, I do use it. It's the backend of my text display library. It is akin to what Rust has, so the display trait, and basically it's to replace show when you want user-facing text to be printed on screen or just be redacted or something like that. So it uses this linear builder as the backend. It's really nice, really nice API.
So, so I was thinking just now that there were a lot of recent changes in GHC to the outputable instance, which is something that also kind of, builds up text to then print at the end. Have you considered or thought about if this could be used by GHC?
I know that I tried to use this linear builder as a backend for Pretty Printer library, and it worked out quite nicely. I think it's been like faster by 30% or something like this.
Okay, we are already a bit over time. Maybe one more question, if there is one.
If this works finely with text, can we have the same package for byte strings?
So this package works for both text and byte string, right? You can run buffer and get either text or byte string.
Yeah, but can consume byte strings?
Yes, it's possible. There is an open issue for this. Someone has to do it.
Okay. Yeah, thank you so much, Andrew.